Hello. So my voice is clear, right? Okay. Hello. Good afternoon. So now this is fine. Okay. Okay. So I welcome you all to the week 10 discussion of Smart Grid Basics to Advanced Technologies. I am Adyasha Sahoo, a PhD scholar from Department of Electrical Engineering, IIT Roorkee. So in the previous week, we saw the lab demonstration of power generation from PV and wind, and then we saw the cell balancing method. After that, we saw some architecture of AC microgrid and DC microgrid. So we'll dive into more details of the control logics that is done for AC microgrid, DC microgrid, and also hybrid AC-DC microgrid. So for that, we are performing this all these studies using the real-time simulation platform that we discussed in the previous week also. So using those RTDS and OpenRT softwares. So we are able to simulate the basically uh, control logic, and as well as we are able to add the hardware to the in addition to the simulation system. So basically here we feed in our test system in the RTDS, and then we use hardwares components such as we had seen IGBT stacks for inverters, gate driver circuits, and power grid emulator, and various other components also. So those can be actively integrated to them. So they can communicate between those hardware devices and the test system to basically simulate those scenarios, various scenarios in real time. So there we had seen that it can either be CIL, which is a controller in loop, or the other one was HIL, that was in hardware in loop. So the controller in loop demonstration we had seen for the SOC balancing circuit in the previous week. So there we had the controller which was coded in the DSP software, and it was basically that's why since the controller was coded in the DSP, it was called the controller in loop. And the other two, which were the power generation from PV and wind. So there we had connected various hardware components such as your inverters, filters, driver circuits. Then there was the grid emulator and various other components. Those were interacting in real time with the test system, which was embedded on the RTDS cards, and we were able to perform the simulation there. So next we will see various case studies starting with a AC microgrid. So here you can see we have the grid connected AC microgrid. So this is the PCC, and we have the grid this side. Now at the PCC we have a AC microgrid connector. So we have a PV source which is connected to this AC bus basically using a converter, AC DC converter, DC to AC converter. Then we have a AC load of 0.5 megawatt, The PV has a maximum power of zero point 0.4 megawatt, then a 1.25 MVA diesel generator, and we have a battery, lithium ion battery, again connected using a DC-AC converter. So, if you remember in the earlier lectures, we had studied about the grid forming and grid feeding inverters. So now, since this is a grid connected setup, so you have the so all these converters connected with the battery or the PV, they require reference signals to function. So they require P and Q reference signal. And since it is a grid connected system, the P reference is provided by the grid. And now for the Q reference here, we have the DG. So for a grid connected system, the DG provides the Q support, reactive power support. And if we consider a islanded microgrid, then either if you have a grid forming inverter, it can give you the reference signals. But if you don't have them, then in those cases, the DG will be providing with you both active and reactive support. So we have two modes of operation, grid connected and isolated mode. So in the grid connected mode, the PV will always operate in MPPT. That you need to see. And then depending upon the basically conditions of the PV, the battery may either charge or discharge. Then the diesel generator will basically help in voltage regulation using or by providing reactive power support. And let's say if there is an yes. Yes, PV can basically, if you have connected a PV source, so what you want, you will always want to extract the maximum power that is available from the PV source. Now, if you have a grid with you, then you can always operate it in the MPPT because if there is excess generation, then it can utilized in the battery. But if it is in an isolated mode, it will again depend whether the battery has the capacity to charge or not. So let's say uh, in the isolated mode, your battery SOC is let's say already at 0.95 or 95%. Then and let's say the load is point yeah, will be let's say zero point 0.2 megawatt. And we saw that the PV was for MPPT, it is giving zero point 0.4 megawatt of power. So and this is a islanded condition. So the PV will provide power to the load. So zero point 0.2 megawatt is deducted and you are left with a zero point 0.2 megawatt of power. Now, what option do you have? You have to charge the battery using this zero point 0.2 megawatt of power. But since the battery SOC is already near about fully charged, you cannot basically utilize this zero point 0.2 megawatt of power. And you always need to ensure the power balance. So that's why the PV has to then operate at a point which is not the MPPT condition. That means here the PV has to inject only zero point 0.2 megawatt of power, which can be used to only satisfy the load since you do not have the battery capacity. Okay. Yes, so the main point is in the grid connected mode, PV can always operate in the MPPT mode, but in the isolated mode, the PV will operate or not operate in MPPT mode. That will be detected by the battery SOC limit. And here the DG is operating in the isochronous mode, means it is providing both active and reactive power support. Because it may happen that the PV donor is generating less than the load requirement, then in those cases you have to use the DG to supply the active power, and it will also help in supporting the voltage through the reactive power. Now again, the battery will charge or discharge. We'll see it basically if you have your PPV is greater than P load, so the battery can charge. And if your PPV is less than the load demand, then the battery has to discharge. So here you have two options. Either you can discharge your battery or the DG can provide the power. So we'll see what is the logic basically which has to step up first, the DG or the battery. So this is the inverter control of a PV battery. So depending upon this PAC ref and QAC ref, whether it is a grid connected or a landed mode of operation. So if it is a grid connected mode, then PAC ref will be provided by the grid and Q reference will be given by the DG. But if it is islanded mode, then both these reference will be given by the DG. Now, the controller here will basically try to minimize the error by comparing it with the reference signal. And then basically, we are calculating this in the DQ frame. So we then transform it to the ABC frame, and then we calculate the required pulses or the D2 cycles that are required, and those are communicated to the inverter. So the first case, we have a grid connected mode with no uh, distributed energy resources. Means you have no PV basically here. So you see, this is the PPV, which is 0. Then the P load is 0.5 megawatt. Then this is the grid connected mode. So obviously P by the DG will also be 0. You see it is near about in the order of 10 to the power minus 10. Then battery is also 0 here, power from battery. So the load of 0.5 megawatt is satisfied from the grid. So you see here P grid is some 0.5 megawatt. So in the grid connected mode, the grid is providing the power if the PV is absent. And but yes, in the next case, we see that the load has now increased. You see the P load has increased from 0.5 megawatt to 1 megawatt. So to supply this additional power, the P grid has again increased to 1 megawatt. And this is displayed here. And I don't know how clear it is, but this is 1.00 written here. Again, you have no DER, means no PV. So PPV is 0 here. PDG is 0 here since it is the grid connected mode. And the battery is also 0. Now in the third case, we have the PV. So since this is the grid connected mode, so the PV will always be at MPPT. So hence the PPV is at 0.4 megawatt. Now PDG will be 0 since this is the grid connected mode. P load is 0.5 megawatt and P grid is 0.42 megawatt. Now if we know all this, can we calculate the battery charging or discharging condition? So you have PDG basically, PDG plus PPV plus P grid. So these are your generating sources. So this will give you the total generation. So how much is it? Right, 82, right? Now what is the load? It is 0.5 megawatt. Now what is the difference? Summation P gen minus P load. That is coming to be positive 0.32 megawatt. So should the battery charge or discharge this 0.3 megawatt of power? Whether the battery will charge or discharge? So you have excess generation here, right? P gen is greater than P load. 0.82 is the total generation. 0.5 is your total load. So you can use the excess generated generation to charge your battery. So and by how much? By 0.3 megawatt, 0.32 megawatt. So here you see it is written as minus 0.30 megawatt. So you see here it is written that if P battery is negative, then it is in charging mode, and if it is positive, it is in discharging mode. So here it is being displayed as minus 0.3 megawatt means the battery is here in charging mode and the amount of power is zero point 0.3, which is matching with this calculation. And here you see the DG is in voltage regulation mode because here the QDG is 0.5 megawatt. That means that QDG, it is injecting. So basically, if you see the flow of power, this is injecting power to the grid. Now battery in this condition, it is charging, so it is drawing power. The grid is injecting power to the bus, and obviously load is drawing the power here. And the DG, basically, it is not withdrawing any or withdrawing or injecting any power to the grid. So it is near about zero here, but it is supporting the voltage by basically injecting 5.5 megawatt of power to maintain the voltage at this load bus. Load bus is regulated by DG. So is this clear? Okay. Now in the next case, so here again, the PV is at 0.2 megawatt and PDG is 0 since this is grid connected. Load is 0.5 and grid is 0.02. So what should the battery do? Charge or discharge here? Which is near about 0, we can say. What will happen? If the load is 0.5, PV is generating 0.2, and your grid is basically 0. So what should the battery do? Point 2 or 0.3? Yes, and it is positive, right? So plus 0.3 megawatt, and you see whether it is charging or discharging. Yes, it is discharging. So it is injecting the power required to supply this 0.5 megawatt load since the PV is at 0.2 megawatt. And we had also seen that if this is positive, it is in discharging mode. And another thing here, although the P grid is 0, the Q grid is non-zero here. Q grid is minus 0.5 megawatt, means it is absorbing power, reactor power. So previous cases all were the grid connected mode. Now we will see the isolated mode. So in the isolated mode, so always the both P grid and Q grid will be 0. They both will be 0. Load is 0.5 megawatt here. And PV is in MPPT. MPPT at a power 0.4 megawatt. And PDG is also 0.4 megawatt. So battery will be 0.1. Your total generation is from PV and DG, which is zero point 0.4 plus zero point 0.4, 0.8 megawatt. Yes, it is point minus point 0.3. So basically, it is charging. Similarly, in the next case, again, we have PV at zero point 0.2 megawatt. Grid is not there. So both P grid, Q grid are 0. Same zero point 0.5 megawatt of load. PDG, PDG is 0, near about 0. So what about P battery? What will be the case here? And charging or discharging. And another thing to note here is in the isolated mode, the Q supplied by the DG will be non-zero. You can see here UDG is minus zero point 0.4 megawatt because in the we discussed in the islanded mode it will give both P and Q. So here it is also minus zero point 0.4 megawatt since we do not have the grid here. Now in the case 3 again we see PDG is zero point 0.5 megawatt but the load has increased to 1 megawatt and PV is at zero point 0.2 megawatt. Grid is absent. So what is P battery? Mm, yes. So because when the load increases by zero point 0.5 megawatt, all the three resources, that is battery, PV, and grid, they are providing power to the load. This was the AC microgrid scenarios. Now we will see for a islanded DC microgrid. So you see this is the DC bus and here you have connected with the microgrid is consisting of PV panels, DGs, batteries and supercapacitors connected through the respective converters. Here you also have wind which is connected through AC-DC and then DC-DC converter. Then you have load. So this we have seen that here we are using a hybrid storage system that is both battery and supercapacitor. So do you remember whether battery was a high energy density type or a high power density type storage? And what was the concept of hybrid energy storage system? Can you recall? That was the hybrid AC-DC microgrid. Uh, I am asking about energy storage, hybrid energy storage concept. Hmm. No, it is something related to this battery and supercapacitor. So they are forming a hybrid energy storage type. So battery is also a type of storage, supercapacitor is also a type of storage. So why we are then using two types of storage technology in a single system? Yes. So what we do in a hybrid energy storage system is because the energy storage system will either have a high power density type structure or a high energy density type structure, depending upon its technology. So what we try to do, we try to combine two energy storage technologies, one with high energy density type and one with high power type. So we use a high energy density technology, storage technology, and a high power density technology so that we can use them for different applications. So here, which one is the high energy density among battery and supercapacitor? Supercapacitor is a high power type, and battery is a high energy type. Yes, that means it can store charge for greater time interval efficiently. And the supercapacitor can charge or discharge in small time. Means very quickly it can charge or discharge. So now depending upon the SOC and all, we'll see different scenarios for the DC microgrid again. So here what we do, first we check whether PG is greater than P load. Now if it is yes, so Y for yes, that means if you have excess generation, if in this side PG is greater than PL, in this side PG is less than PL. Now if you have excess generation, what you would like to do, you would like to charge your battery with the excess generation. Now whether the battery can charge or can charge or not, it will depend upon its SOC. So next what you do, you check the SOC of the battery. So here you are checking whether SOC of battery is greater than 90%. So if it is greater than 90%, then you cannot charge the battery. See, so here, if it is yes, then you cannot charge. That means there will be no MPPT mode of operation. So PV means the resources PV and wind will be in bus voltage regulation mode, and the battery will neither charge nor discharge. It will be in idle. But if the SOC is less than 90, 80 or 70, something like that, then both the resources can be in MPPT mode. PV and wind can generate power in MPPT mode, and the excess renewable energy can be stored in the battery so the battery can charge. Now coming to the case where we have less generation, that is PG is less than PL. So if PG is less, so what you would like to do, you would like to discharge your battery to supply the load, right? So whether then you will check the SOC of the battery, whether the SOC is less than 40% or not. So if the SOC is less than 40% means the battery cannot charge. So if it is yes, then here BESS cannot charge, cannot discharge basically, cannot discharge means it cannot provide power. So what you do, you then check if you have DG with you. to then supply the power mismatch. So if the DG is available, yes, then we check whether the available power with the DG is greater than the power mismatch. So here you're checking if PDG is greater than P load minus P generation. So if it is yes, then you can use this excess power from DG to charge the battery. If it is no, then we will see the algorithm D here. So if here what you have, PDG is less than PL minus PGen, means you cannot supply your all the loads. You have to go for load curtailment here. You do not have sufficient generation with you. So what happened here? You checked the battery condition. So you found out that the battery does not have enough power. Battery SOC was 40%, less than 40%. Then you checked DG. Again, DG was not available. So what you will do, if you have, then you have to go for load curtailment. Now, which load you will curtail, that will depend upon the priority of the load. So some loads are crucial. Yes. So we know that some loads are crucial. They are more important than others, such as your hospitals, airports, military stations. So we always want that these kind of loads are always on. They cannot be curtailed. So then the load curtailment is again depend upon the SOC of the battery. So we are at D means the SOC is less than 40%. So now how to use this as a 40% SOC to provide the loads. So then you check is the SOC less than 30%. So if it is no, that means your SOC is somewhat between 40 to 30%. So if this is no, so here your SOC is between 32% 40%. So the battery can provide power to the critical load plus some non-critical load, to non-critical load. But if the battery FOC is even less than 30%, that is here, then you again check whether it is less than 20%. If it is here, it is between 20 to 30%, then you can supply the critical load plus one non-critical load. But again, if the SOC is further less than 20%, that is here, it is less than 20%, then you can only supply the critical load. Is this part clear? Okay. So this was the algorithm D. Now what was A? In the A, we were checking the DG condition, whether DG is available or not. So if the DG is not available, then we come to A. So similar to that means you have to again similarly use the battery SOC. So you need to use BESS to supply the load, and similar to the procedure in the D, here also you check the SOC of the battery, and if it is less than 40% but greater than 30%, then you supply the critical and non-critical loads. And if it is further less than 30%, then you are only supplying the critical loads. So the difference between algorithm A and algorithm D is in the A condition, the power support is only being provided by the BESS. So in both A and D, you have PG less than P load. So in A, the mismatch is supplied by discharging battery. But in D, both DG and BESS are supplying the power to loads. That is the difference between this A and D. Is this clear? So, similarly, you can see the various waveforms corresponding to this isolated DC microgrid system. So, yes, so this is the load you can see. So, it is at 0.3 megawatt, but at this instant, what happens is your load is dropping from 3 megawatt to 2 kilowatt. Basically, this is in watts. So, from 3 kilowatt to it is going down to 2 kilowatt. And in that case, again, your grid, you see, grid is also coming down to somewhat below 2 kilowatt. And this is the curve for the SOC of the battery. So when there is, and you also have the battery with you charging and discharging. This is by this plot. And this is your P grid. And this is the DC voltage. So you see, even if there are some transients, the voltage at the DC bus is maintained at around 380 volt. Now we are trying to interconnect two DC microgrids. So this is DC microgrid 1, this is microgrid 2, and this is DC bus 1 and DC bus 2. So we are forming an interconnection of two autonomous DC microgrid here with PV, battery, and loads of their own. So now we will see how they can support each other. So next thing was the coordinated voltage control scheme. So what happens in this thing is basically for controlling or coordinating the voltage, you need to manage the reactive power. So what it is usually recommended that we keep reserve reactive power reserves in the system, which can be activated whenever there is a voltage violation. So these reactive power reserves can be activated to mitigate the voltage violation. So what is this Q reserve? It can be basically calculated by the maximum uh, Q that can be provided by the generator and the current operating condition of the Q gen. So let's say the maximum is 0.5 MVAR and currently it is at 0.3 MVAR. That means it can provide additionally zero point 0.2 MVAR which you are not using. So the reserve is 0.2 MVAR here. Now, why we are keeping these reserves? Because it is not always recommended to transfer the reactive power over long distances. Since voltage is a local phenomena, we want that the Q reactive power is activated only where in the area there is the voltage issue. So, because transmitting reactive power over long distances, it may lead to additional losses in the system. So, and also it may limit the transfer capability of P. So, what it means that let's say you have a transmission line with certain uh, VA limit, right? That is the apparent or S limit. So, that is nothing but P square plus Q square. So, if you use this line to transmit the reactive power also, that means if you increase the reactive power due to its S limit, the active power transfer capability will decrease. So hence, what we do is we keep reserves and activate the reactive power locally. Now, what are the various reactive power sources in the system? Can you name various reactive power sources in our system? Yes, inductors and capacitors, synchronous generator, yes. Anything else? Yes, the Stratcom and other FACTS devices, yes. Uh, line charging capacitance, basically the transmission line. If you remember the modeling of medium length transmission line or long length transmission line, so in the medium length, we have the pi section model for the transmission line. So this is the Z, which is R plus JXL, and here you have minus JC. So these capacitance and inductance of the transmission line, they can also contribute for the reactive power in the system. So hence there are various sources of system. So now what we can do, we can divide these Q sources into two types, static and dynamic. So what is the difference between static sources and dynamic sources? Yes. What about STATCOM? Okay, so how do we label whether a source is static or dynamic? Okay, that is one way. Other thing is the static sources, they do not allow uniform control of reactive power over a range. What do I mean by that? So this L and C, they can provide the reactive power only in steps, right? Let's say depending upon their rating, they can provide 5 MVAR, 3 MVAR or something like that. But if I want something like 5.5 MVAR, it is difficult to basically extract integer type of 5.5, 6.3 type of thing from the combination of L and C. It will depend upon their rating. But in the dynamic where you have synchronous generator and all, so it allows smooth control of reactive power over a range. You can basically get whatever reactive power support you want from them. And another thing is mostly this dynamic reserves, they can be activated in a short period of time. That means they can instantly improve the voltage. Whereas in the static sources, there they will take some time for their operation. So, and also another type of static source is your OLTC transformer, on-load tap changing transformer. So all these cannot instantly support the voltages, but the dynamic reserves, they can be activated instantly and within seconds they can improve the voltage. Also, static are costly and you need to install them additionally in the system. But again, this dynamic reserves can also be provided by the renewables equipped with battery. So, wind farms and also your PV plus battery system. So, these all are various dynamic reactor power sources in the system. So, since I said that dynamic can be very can be activated in a short period of time. So, what we do is try to maximize these reserves so that whenever there is a contingency in the system, these can be activated instantly. So, here we optimally utilize the different compensating devices to increase the reactor power reserve. What it means, so let's say you have a time period of operation, right? 1 hour to let's say 5 minutes. So if what you try to do, you try to keep your dynamic reserves more to the real time, more near to the real time. So in these cases, I try to save dynamic sources because there you have to do the corrections in less amount of time. But if I have a greater time period, that is something like 1 hour, so I try to utilize my static devices such as your OLTC and inductors and capacitors to manage the voltage. So in long period of operation, we use the static, and for near real-time operation, we use the dynamic sources. So again, these can be centralized or decentralized. So this we have seen in the previous lectures also that in the centralized, what will you do? Everything is connected to the central station, and the central station will basically compute the reactive power required from various sources, and it will give those control signal to the each of the sources. In the decentralized is what? It will function depending upon whatever control logic you have fed into them. So, yes, this OLTC transformer, it can basically what it is usually situated at the head of the grid, distribution grid, or at the substation. So basically, you have a distribution grid like this, radial connected. So usually, so the OLDC transformer will be at the head of the feeder. So we know that, let's say, if the voltage here at V1 is, let's say, 1 per unit, then the voltage at the tail end is, let's say, there will be drop in each of these lines. And then finally, let's say the voltage here is somewhat at 8.5, let's say, at this bus. Can you mute yourself, Devansh? Look at the card. Yes, thank you. Yes, so let's say the voltage at this last bus is 0.85 per unit, which is below the acceptable range. So what we can do, we can increase this V1. Let's say we increase this V1 to 1.1 per unit, so that after there is a drop, so here the drop was how much? So if I increase this, then this V2 will be 0.95. So your voltage can be improved that way. So basically here you have various tap positions on the transformer. Mostly there are 16 positions, and each position can change the voltage by 0.00625 per unit, and that is in both positive and negative direction. Means if this is tap position 0, so 1 plus 1 minus 1, 2 plus 8 minus 8. So either you can increase by this 0.00625 per unit value, or you can decrease the voltage also. That is in the both the direction. Then other sources are your DFIG, or that is your wind farm, and DStatCom, and also we are using a DC microgrid. So utilizing all these resources, we'll see how we can coordinate the voltage. So this is the test system. You see there are 33 it is a 33 bus test system. You have buses from 1 to 18 here, again 19 to 22 and 33. So various sources are connected here. You see the OLTC is OLTC. This is the OLTC connected at bus 1, and then we have the DStatCom here. DStatCom connected at bus 22, and we also have a wind farm connected at the same bus. Then this is the DC microgrid, which is connected at bus 5. Okay, I don't think any other resources are connected here. Yes. So depending upon the requirement of reactive power, we can divide the operating states of the grid into three states. So in the steady state, so if in the steady state, the voltage is within the limit, means the voltage will lie between zero point 0.9 to 1.1. And to maintain this voltage in this range, if the Q requirement is less than 40%, Q requirement is less than 40%, then we say that the system is in the steady state. Now from this steady state, you can either go to the dynamic state or you can go to the transient state. Now, if your voltage is greater than zero point 0.9 and the Q required is greater than 40%, then you move to the dynamic state. So to improve the voltage, your in the dynamic state, the Q is fixed at 40%. But if your voltage is less than zero point 0.9, that is, zero point 0.9 is your threshold. It is less than zero point 0.9 means the system is in unstable state or the transient state. So you need to give full support. That's why Q is 100% here when the voltage falls below 0.9%. Okay. Similarly, from this dynamic state where we fix the Q at 40%, if the voltage again falls below zero point 0.9, we go to the transient state from here. And if the voltage is greater than zero point 0.9 but the Q required is less than 40%, so we move to the steady state. Similarly, from the steady state, transient state, so basically in the transient state, there are violations, serious violations in the voltage. So we provide full Q support of 100%. And from this, if the voltage is within the range that is greater than zero point 0.9, And if the Q requirement is less than 40%, you can go to steady state. But if the voltage is greater than zero point 0.9, but the Q required is greater than 40%, then you can go to the dynamic state where the Q will be fixed at 40%. So these are the three operating states of the grid. Is this clear? Okay. So we'll see what is the scheme here. So what you will do, first you will check whether the voltage is in the acceptable range or not. So if the voltage is not in the acceptable range, means it is below zero point 0.9 or 1.1. So that means we are in the transient state. So you see this is the transient state. That means you need to provide 100% of reactive power support. And how, that we will discuss again. And but if the voltage is within the range, then either it can be in the steady state or in the dynamic state, so that we will check. So after the voltage is in the range, we check whether the voltage is at 1. So if the voltage is at 1, so 1 is the most favorable voltage condition, flat voltage profile that we call. So you do not require any Q. So you see, if it is at 1, the Q is 0. But if the voltage is not 1, then we check whether the Q requirement is greater than 40% or less than 40%. So if the you check here, is the Q required less than 40%? Yes, then you can go to the steady state we see. And if the Q required is greater than 40%, then we fix the Q to 40% and it will go to the dynamic state. Yes, dynamic state. Now, in the transient state and the steady state and dynamic state, the master and the slave function is for a role of the three resources that we're using. That is your OLTC, that is your DC microgrid, and your STATCOM, that is your D STATCOM or your wind. So their role is different. So what is this concept of master and slave? So basically, you see, we have three sources with us and we are activating them for correcting the voltage. So first thing is, we do not want all the three sources to act at the same time. We do not want the sources to act at the same time. Why so? So basically, we try to see whether the voltage can be corrected in steps. So in case of transient state, it is a emergency state, right? Your voltage is already below 9.9 or it is greater than 1.1. So what you want instantaneously to improve the voltage. So whether dynamic resources or static resources can be used to improve the voltage instantaneously. If you want to improve your voltage in a short period instantaneously, so which resources are helpful, dynamic or static? So dynamic resources can improve the voltage instantaneously. They can be also activated in a very less amount of time. So among this wind and D statcom is the dynamic resource, and hence it is asking acting as the master. So this is M for master. So whenever the voltage is beyond the limits, so what we do, we instantaneously activate the master, which is the dynamic source, to improve the voltage, and after that we then activate the static sources of OLTC or DC microgrid. That is when voltage is inviolating. But if the voltage is within the limits, then what we try to do, we try to correct the voltage utilizing static sources and reserve the dynamic resources for transient states. So here OLTC, that is the static, is the master, while depending upon in the dynamic state, the D-Statcom, DC microgrid and all, they are the slaves. So what are the operating stages? It is basically first stage we are identifying the condition of the grid. Basically here you are identifying the condition of the grid here. After that we are checking the availability of the device and checking whether they are in the master role or slave role. And in the third stage we are introducing a time delay in operation. So time delay in operation is introduced between the master and the slave. Now we will see its operation with respect to the time delay. So again, we are checking the condition, and if the voltage is within limits, then we will see whether it is in steady state or dynamic state. So after coming here, we basically apply the master, which is the OLTC. So you can either increase the tap or decreasing the tap, whether you want to increase the voltage or decrease the voltage. Now, after going to the OLTC, then we have the DC microgrid as the master. So it will check if the delay is has passed. Means after OLTC, you activate the DC microgrid after a certain delay. So if no, then you do not give any Q. But if the delay period has passed, then you check the voltage. If the voltage is at 1 per unit, you do not require any Q. But if the voltage is not at 1 per unit, you then check the required reactive power. So if the reactive power is available, it will supply this QDC microgrid. It will supply, and if it is not, then it will supply according to the need. Now, after this DC microgrid, the slave lastly is the STATCOM. So it will check whether it will basically be activated after OLTC and DC microgrid, and if the delay period has not passed, it will wait. It will not provide Q support. Again, similarly, it will check for the required reactive power support, and it will be then in the dynamic state or in the steady state. If the Q required is greater than 40%, then it will be in dynamic state. If it is less than 40%, it will be in steady state. So this is the steady state operation here. So yeah, this is the voltage here. You can see the voltage is above 1 per unit here. So what is the advantage here is in the proposed technique. Uh, yes, you can see this is the OLTC position. So without the coordinated voltage support, there was only one change in the OLTC position once. But in the proposed technique, the voltage position was varied twice, the blue line basically. And similarly, here this DC microgrid is activated after the OLTC. So you see, after a T delay here, the DC microgrid is basically stepping up to correct the voltage. And similarly, here also you have the delay given here. So this is nothing but this is the zoomed in version of these plots basically. So you can see with the so this is the in the last figure here. This is the time delay that you are introducing in the x-axis, and in the y-axis, if you see the voltage blue is 0.98. This is 0.98, which is the best voltage, but without CVC, the voltage was at 0.975. So using the coordinated CVC, we can improve the voltage further to zero point 0.9 per unit. And here it implies that the control is introduced after some time delay and also quickly. हेलो कार्ड आया है क्या हेलो मेरा ना मीटिंग चल रहा है आप 6 बजे तक आ सकते हैं इलेक्ट्रिकल डिपार्टमेंट आप इलेक्ट्रिकल आ जाइए उधर तो कोई नहीं है और क्या चाहिए कुछ मतलब आधार कार्ड वगैरह कुछ चाहिए या नहीं अच्छा कल कल डिलीवरी कर दीजिए फिर मुझे लगा ठीक है हाँ yes lastly then we have multi-parallel inverter system. So similarly, as we know, we can expand the generation resources by adding them in parallel, and also we can do that for transformer. So same thing we can do for the inverters also. So in the inverter, you see this is the inverter 1, inverter 2, up to inverter n. So this is the total current that is flowing to the grid side, this I grid, which is the summation of the individual inverter currents. So from I equal to 1 to n, I to I will give you the total current that is being injected to the grid side. So this I grid is having two components, common component and interactive component. Now the common component is which is at the grid side. So this is the common part of the I grid, and the interactive component is between these inverters. I interactive. Which is I interactive is which is basically flowing through the inverters. and this is flowing on the grid side. So basically, you see, this is the inverter 1, this is inverter 2, operating at voltage V01 and V02, and then supplying it to the grid. Through the grid impedance, this is LG, and this is the grid. So this will be I21, this is I22. So what I can write this component I21 and I22 as a function of the voltage at the inverters V01 and V02. And this G parts can be calculated using the superposition principle. So what the superposition theorem says that when you have multiple sources in the circuit, you can activate them one at a time and then you can add the effects for each source. So what you can do, you can short circuit the voltage 2 and calculate the effect due to inverter 1, and similarly then you can short circuit 1 and calculate the effect 2 and basically sum them. So if I say this I21 is G11 times V01 plus G12 times V02. So this part is due to the voltage V01 in the inverter 1. So this is the common part. But this part of the current is the interactive part, which is due to the V02, that is voltage of the inverter 2. Similarly, I22 is G21 V01 plus G22 times V02. So this is common, while this part of the current is flowing due to the interaction of inverter 2 with 1. So this is the interactive current. So this is just again the same representation here. Now, for getting stable currents without oscillation, basically we see the characteristic equation and check whether the poles of this are lying on the right hand plane of the S plane or not. So this we know from the concept of control system, that if we plot the poles of a system and if they have the negative real part, if the poles have negative real part, then it is a stable system. So that means this portion, if the poles lies in the left hand side of the S plane, so this is stable. And if poles have positive real part, that is unstable system. This is unstable, and poles on the y-axis, that is here, that means zero real part. That means only you have the imaginary component there. It is a marginally stable system. So if you draw the response here, what you see that the in the stable system, the oscillations die out with time. So the amplitude decreases with time so that the system becomes stable. In the unstable system, you get oscillations with increasing amplitude. So amplitude increases and it is unstable. And in the marginally stable system, you get sustained oscillations. That means of equal amplitude. Oscillatory response. Now, lastly, we will see that introducing this nonlinear loads and various electronic components introduces various harmonics into the current and voltage waveforms. So the sources are your nonlinear loads, your polyphonic switches, converters, and what are the effect? Basically, due to this nonlinear loads, the harmonics are being injected back to the supply side. Then they can also interact or interfere with other power system equipments present here, and they can also lead to additional losses in the various components, and they can also interfere with the power with the telecommunication lines and cause error in the meterings. So these are some of the ill effects of harmonics that we can see. So this is the normal one without harmonics. And now this is the voltage sag. That means the voltage you can see in this portion has reduced. This is voltage swell. So the voltage has increased here. Then another ill effect is your interruption. That means the voltage is absent in this part. And for current, similarly, this is your normal one. So the nonlinear loads can introduce harmonics, you can see here. Then I notch is basically this sparks you get here, peaking current that you get here. That is another irregularity in the current. And lastly, due to the unbalanced nature, you can also get this type of current waveform. Then this is again phase jump. So you see in up to this you had blue, red, and yellow three phases, but after this part you do not have the blue phase. So one phase is absent, and this is also a waveform for a certain type of harmonics. So similar to this nonlinear loads you can see here. So to basically mitigate this harmonics, we can install filters in the system. So they are passive, active. Then the active we can classify them as shunt or series. And lastly, we have a combination that is shunt plus series active filter, which is your unified power quality conditioner UPQC. So in the passive one, you see there you have the passive elements RLC. So they can be connected in shunt, in series, or in a combination of shunt and series. So the main disadvantages of them is again due to their bulky size, and they are also fixed quantities. They cannot adapt according to the system. So we move from passive to active filters, which can easily adapt according to the system conditions because we have your polytronic components used. So now depending upon the connection, they can be of series type or shunt type. And in the UPQC, you are having a combination of both shunt and series active pass filter. So the shunt part is basically mitigating the current harmonics, and the series filters can mitigate the harmonics present in the voltage. So hence you can use the unified power quality conditioner to mitigate the ill effects of current and voltage harmonics. So for demonstration purpose, you can connect a nonlinear load here, and then you can feed in your obviously you have a microgrid here with PV, battery, and wind, and this is the DC microgrid. So this is the shunt filter side. This is the series filter side. So this part will correct the current harmonics. This part will correct the voltage harmonics. So and the shunt will provide a low impedance path for the harmonics to flow out, and then the series side you will have a high impedance path. So depending upon the controller logic, you can ask the calculate the duty cycles for all these converters to basically mitigate the voltage harmonics. Yeah. So this brings us to the Q&A session. The first question is, which of the following is responsible for providing AC voltage and frequency in islanded AC microgrid integrated with battery, diesel, PV, and loads? The key here it is a islanded AC microgrid. Yes, it is DG. We have seen it will give both the P and Q support, or basically both V and F. So the next is DG is capable of what? It will be anyone else? You can type in the chat box also. Yes, this we have seen. Basically, in the islanded mode of operation, it can inject both active and reactive power. Now, the next is the wind generator is processed through which type of conversion system to feed power to a DC microgrid. Yes. So wind is the AC source. You convert from AC to DC. Then you can boost this voltage and convert it to DC to DC. So in a two inverter system with similar inverters, if the current reference of current loop are equal, then which component will exist? Mhm. And yes, two inverters are connected in parallel. Actually, if you see here, so I am telling that the current reference are same. So if they're same, which component will be absent? If IREF1 is equal to IREF2, then which component will be absent or which component will be present? This one is the interactive. Hmm. And if the reference are this IREF1 is equal to IREF2, then which component will die out? It will be zero because these are equal and only common current will exist. So only common current will exist. Yes. Now the purpose of a DG in a AC microgrid is what? AC microgrid, let's say any condition, consider both grid or but consider both the scenarios. So basically, it can regulate the voltage in both grid connected and islanded mode. It can regulate the frequency in islanded mode. It can also supply power during low renewable. So it is all of the above. So that is basically a P support. No, it is an islanded mode. No. So in one case it can provide. No, that's why I told that you can consider both the grid connected and islanded mode, and it can regulate voltage in both the modes, right? In the islanded and grid connected. So battery and capacitor are connected to the DC microgrid through which type of converter? Yes, why so? Basically to allow for the bidirectional flow of power. So either you can charge or discharge a battery. So for that you need to have a buck boost converter. Yes. Basically it will depend upon the voltage between those two buses, no? And let's say this is V1 and V2. So similarly, if V1 is greater than V2, then the power flow is in this direction. If V1 is less than V2, power flow is in the opposite direction. And let's say you want this is your V1. So uh, to get V1 greater than V2, so you need to have the buck operation. And if you want V1 is less than V2, so you can boost the voltage there. V2, V2. Mhm. Interconnection of two local DC grids is feasible for what? Whether you can connect DC grids having unequal voltages or we require equal voltages. Yes. Does not depend upon the voltage level of the DC grids. We can do both. What is the disadvantage of passive filter? Yes. Now, which of the following component of inverter current is independent of grid side impedance. Yes, it is depending upon basically the voltages between the inverters. The grid side impedance will affect the common current which is flowing to the grid side. Now, which of the following is most critical state requiring voltage or reactive power support? Steady, dynamic, transient, or all? Yes, because in the transient you had voltage violations. In these two, voltage were within the limits. Now, which transformation converts AB from ABC frame to DQ frame? Mm, Park actually. Now, identify the current correct statement regarding synchronous generator. Yes, overexcited synchronous generator can inject the reactive power, and underexcited will absorb reactive power. And in normal condition, it is operating at lagging power factor. No, it is UPF. Yes, this is the same question. Now regarding battery and supercapacitor, how they are connected to a DC microgrid. So the battery and supercapacitor, how they are connected to the DC microgrid, whether with a buck boost converter, both of them are connected through the buck boost, right? So that is option C. Yes. Now next is which is not true in case of isolated mode of operation of AC grid. Yes, because it will depend upon the battery association. Then and OLDC is connected between node 1 and 2, regulating the voltage there. So if voltage V1 is 1 per unit and the tap is at minus 10, what is V2? Uh, it will decrease the voltage, no? It is minus 10. A tap position is minus 10, means you are decreasing the voltage from 1 per unit. Mhm. Yeah, it is 0.9375. Basically, one tap position was 0.00625 per unit. So 10 taps will be 0.0625 and it will be minus. So 1 minus this, I think is same. Hmm. So V1 minus for single tap, the change in voltage is 0.0625 and the tap is minus 10. So that is giving you 1 minus no, this is plus. So 1 minus 0.0625, 0.9375. So what is the range of voltage in the transmission grid for steady state operation? No, actually, we allow between zero point 0.9 to 1.1. This is a very strict range, so this is allowed. Hmm. What is not true for parallel operation of inverters? Hmm. Is it not true? No, it is true, no? Hmm. No, this is also true. All are correct. So, so it is none because all are correct. Yes. Which is correct for multi-parallel inverter, parallel inverter operation. It is the same thing. If the poles are in the right half, then it will be stable. No? Unstable, unstable. Yes, this is unstable. Left is stable. So this is correct. Interactive currents. No, this is the common current which flows into the grid. Mhm. And if interactive and common resonance occurs in L filter due to first. So we in the L filter we mitigate that effect, right? So it is basically this is the correct statement. No, non-linear induced harmonics. Is it true? Yes, all are correct. Now for an inverter with a LCL filter to be stable, it is required to ensure the stability of. Yes, but to ensure the stability, we want that Both the control loop should be stable, right? This one, basically, this. So we want both this to be stable. So hence, both that brings us to the end of Q&A session. If you have any other doubts, we can address. NCL filter, which uh, these are the mitigation techniques that we are uh, basically we don't have a LCL type filter. You see, that is the hybrid one, this D part basically. It is a type of hybrid passive filter only. So there, basically, we are trying to mitigate the uh, this two components we had, right, I21 and I22. So the interactive current, they are introducing problems, right? Because we don't want them in our circuit. We only want the common current part. So that can be considered a type of abnormal, that is a thing that is being injected. So to filter out those, either you set this I reference, basically I reference 1 and 2. So if you have two inverters, so we are considering I ref 1 and I ref 2. So we'd set them in such a way using just filters and all, such that this I interactive part goes to 0 and we only have the I common which flows to the grid. What are the reference for these basically these converters here? So you see this is the shunt part, this is the series part, I said. So the reference for the various resources you have. So what IREF basically I should give to this converter logic so that they do not the interactive current between those basically dies out. So okay, anything else? Okay. So if no further doubts, then we'll close the session for week 10 and we can meet again in the next Saturday for week 11 discussions. Thank you for joining. Thank you.